Okay, I think we'll get started. I'd like to, first of all, thank you for attending this session. It's a repeat of a session I did earlier in the week, so the fact that I've had a chance to kind of practice it once, hopefully it'll run a little smoother today. My name is Damien Lindauer. I am the performance manager, the manager of the performance engineering team within the SQL Server development group. In today's talk, what I'm going to be doing is sort of giving you an overview of some of the most key and critical performance enhancements that we've made in SQL Server 2000. Throughout the conference so far, you've no doubt heard many sessions talk about performance in the context of various functionality and services and components, and this is because performance is obviously a critical design point for any application. Again, this session tries to give you an overview of all of the various features that we think are most critical sort of across the board. I want to take just a minute to talk a little bit about WinDNA 2000 and how SQL Server 2000 fits into that scenario. The WinDNA platform is specifically designed to give you sort of a comprehensive set of tools, a comprehensive and powerful set of tools for building web applications. And SQL Server is just one component of that platform. In terms of critical success factors for WinDNA, performance and scalability is key. And my goal today is, again, talk to you about SQL Server 2000 performance. And if you've been following the press and some of the announcements and even things people have been talking about in various sessions up till now, you've probably know that there are many interesting performance-related benchmarks and numbers that have been released over the past few weeks, starting with the Windows 2000 launch. And what I'm going to do today is sort of pull the covers back on what we did internally to sort of achieve those really dramatic results. And hopefully you'll come out here with some insights about how we have architectured things internally. And I should also point out that there are a couple of other sessions that you should, if you're interested in performance in more detail in terms of integration with your applications and how to use some of these features at a lower level, I would encourage you to attend. One of them is a session this afternoon called Building High-Performance Systems with SQL Server 2000, and that is a session which will focus on specifically how to ensure that SQL Server can take best advantage of the hardware platform you're running on, very large disk I/O subsystems, large amounts of memory, SMP systems. So it's a very in-depth and detailed talk. I think you'll find it very useful. And it will tie into what I talked to today. The second session is one tomorrow morning called Building High-Performance Applications with SQL Server 2000. And it's also a good tie-in to this talk, as it will talk about how to actually build your applications, the appropriate data access methods, how to get efficient cache, plan caching and so forth, other features. That session will be happening, I believe, tomorrow morning. And the final session, I think, is very much an important session and one you should consider attending, is building scale-out applications with SQL Server 2000. And that is where we do a very in-depth, detailed analysis of how you actually build an application using some new technology called distributed partition views. So you've probably heard quite a few sessions talking about it up till now. That session is the one tomorrow afternoon is the one where you'll actually get to see real hands-on descriptions of how you build it from the ground up. So with that, let's move on. Real quickly, and I don't want to spend too much time on this, but it's important when we talk about SQL Server 2000 performance to look back real quickly on SQL Server 7.0. 7.0 was a product that was designed, from a performance standpoint, one of the most important things that we did in 7.0 was to build the product in such a way that the server sort of self-managed and self-tuned itself. And the idea was to give the developer the luxury of spending time worrying about building a more efficient application, a lot better design, spending more time at that layer and less time worrying about tuning knobs on the server to achieve optimal performance. Things like the integrated inter-query parallelism, the fact that we did dynamic lock management and dynamic object management. All the things you see here on the slide are things that were done to increase performance in such a way that you didn't have to, as a developer, worry too much about getting the most optimal performance. In fact, to be honest, in most of the benchmarks we do, we rarely change any configuration parameters on the server. We actually, what we do is we spend our time worrying about making sure that we have a balanced system in terms of I/O and CPU and memory, and let the server do its job. So this was a pretty critical design point for SQL Server 7.0. But really, what was most important in our design of 7.0, and I think we've had a number of the sessions on the relational engine improvements and the storage engine enhancements talked about this as well, and that is that we were building an architecture for the long haul, an architecture that was flexible and advanced enough that we could continue to enhance it going forward very quickly, to innovate quickly. And the performance changes I'm going to talk about today are really sort of the result of having a very flexible architecture. The fact that we could make have such dramatic performance improvements in such a short period of time is a testament to that basic design and architecture that we built in 7.0. In terms of our performance objectives, and I'll just real briefly mention that we don't just make performance changes for fun. It's actually quite fun to make performance changes. We like to optimize code and make things run faster, but we really try to focus our efforts on the things that are most critical for our customers and the most critical things that we see in the future that they may run into. It's pretty common today when we have a .com company, for example, or an e-commerce site to come in and say, you know, we want to know about, make sure that your product can handle, you know, our scalability needs or our performance needs, and we'll say, well, you know, how many users do you have today? And they'll say, well, we have, you know, 300 or 400, and we'll say, okay, and then they'll say, but we're expecting to have, you know, 100 times that number by the end of the year. So keeping in mind that what we see today is important for us to focus on that from a performance standpoint, but it's also critical for us to focus on where we think people are going in the future. So a lot of work was done to understand the requirements, and really that's the result of many of the changes that we'll talk about today. Real quickly, some of the specific trends that we see are trends that are fairly obvious. User populations are increasing. The fact that with the web you expose traditional transaction processing systems to almost anyone, whereas in the past they were traditionally closed systems, means that you could have huge user populations generating huge transaction rates, and this obviously means tremendous disk I/O. It means that you're collecting tremendous amounts of data, types of data you never would have collected before. We're collecting data today to do personalization and to customize or target certain customers, and the nature of the data is increasing in complexity as much as the complexity of the queries that need to access the data. And with all of this happening, we're also seeing tremendous increases in network I/O. At the same time, our response times are getting stricter. And the real solution is we need to be able to scale up our performance, or at least in terms of taking advantage of resources on single systems. And we also need to find ways to be able to incrementally add performance and scalability by scaling out our solution. So those are the things we're going to talk about today, and I'll kind of go through each one of these in terms of the performance challenges and then talk about the things we did inside the product to address them. So the first performance challenge as I see it, or as we saw it, was this issue of increasing disk I/O. And one of the most critical points here I want to make is that it's a given that we're collecting more data, and it's a given that we have to plow through more data to get the answers we need to do our business. The critical part of this is for us to be able to take advantage of the very advanced and new features of I/O subsystems today. They're getting larger, they have more advanced controllers, they're more advanced interactions with the host system. And so the really critical thing here is how do we take advantage of that to make sure that the software isn't the bottleneck, that we're really driving the hardware to the potential. And so I'm going to walk through some of the things that we've done, and you see a slide up here with some of the basic, some of the most critical things that we did. One is that we basically did work to improve our scan performance, the basic operation of plowing through lots of data on the disk and be able to pull it back into the server to process. Also tied into that is improvements in our read ahead. We did work internally in how we schedule asynchronous I/O to make ourselves more efficient on these large I/O subsystems. And tied into I/O is things like how we handle memory and checkpoint processing and how we deal with text or blob data. So let's walk into these in more detail and talk about some of the things that we did internally in terms of these solutions. As I mentioned, we did a lot of work in our scan performance. We actually in 7.0 we built a very advanced algorithms for doing just basic scans, and at the same time we built support for inter-query parallelism, so the ability to be able to divide a particular operation amongst multiple CPUs to take advantage of the system. And that inter-query parallelism plugs into the scan functionality, so we built code, we call it the parallel page supplier, which actually pulls the data off the disk in the scan operation and then passes it between the various consumers that are running of the scan operation that are running on the different CPUs. So the scenario in 7.0 is that you see here we have a dual, sort of a simplistic representation of a dual processor system, and the SDS stands for the scan descriptor, which is the consumer of the scan. And in 7.0 what we would do is we would sort of, when we needed pages to supply the consumer, we would take a trip through this parallel page supplier, which is essentially a critical section. It's a place where we synchronize access to the pages as they're being pulled off of the disk. And we would take a trip through this critical section, and while we were there, we would go get a page, an 8K page, to feed back to the consumer. But at the same time, we would maybe do some work. So we would be required to sort of pay for the price of getting the page by maybe doing some read-ahead I/O. And once that consumer got his page, the next one would take a trip through the critical section and get its page. And the idea was that you're sort of feeding the consumers as fast as they can consume these pages. Well, with I/O subsystems getting faster and with more and more CPUs being available on S&P machines, we realized we had to make the process of synchronizing the access to the through the parallel page supplier more efficient. And so what we did was essentially we took that piece of code and we optimized it. We removed things out of that critical section that didn't need to be there, so that we could have less contention in that part of the code. And what we basically did was, by shrinking it, we were able to take certain things out of the critical section that had been there before. For example, issuing read-ahead is now done outside of the critical section, which means that we can be inside the critical section less time before the next user can come in and do some work. And so we take a trip through it, we get some work to do, which was some I/O. We do that outside of the critical section. We also, the other thing we do is instead of just one page, we actually grab 16 at a time now. So we get a lot more work done through one pass through this serialization point. And in the example here on the screen, you see that the second user comes back in again. He also goes through the critical section, gets some pages, and maybe issues some I/O, and he sends these 16 pages back to the consumer as well. While he's doing that, the other consumer could still be working on and working with some of those pages. So you have a very efficient mechanism for feeding the consumers of the parallel scan. So in summary, again, you spend less time in the critical section, which is obviously good for improving SMP scalability by reducing the serialization point. Read-ahead is issued outside of the critical section, which again improves the concurrency of the parallel page supplier access. And again, the most important thing in my mind is the fact that we feed larger amounts of data at one time to the consumers, so we get fewer calls. You basically get, instead of 16 calls through to get the same amount of data, we only go through once. Another area in how we process scans that I think is pretty cool is the fact that we have a feature called merry-go-round scans. And in order to describe to you what that is, it's good to look at the scenario where you don't have a merry-go-round scan. In this particular example, we have a very large table. And when I say very large, I mean so large that there's no way that it could fit in memory. In fact, only a small percentage of it could probably fit in memory at one time. In this example, a user comes in, he issues a scan. He scans 25% of the table, let's say. Second user comes in the system, issues the same operation that causes the same scan, and that user is starting to plow through the data while the user one continues on. And what you end up with in this scenario is disk thrashing. You you have no cache effect of the fact that the user 1 has started to scan the table. By the time user 2 gets to the same point, the pages have already been kicked out of the cache and the disks are thrashing. And this is a scenario that can occur if you have multiple user scenarios issuing queries that will affect these very large scans. So the merry-go-round scan scenario for SQL Server 2000 is that it's the same issue. User 1 comes in, scans a portion of the table. In this example, 25%. User 2, when he comes in, and he will realize that someone's already scanning that table in the same way, and he'll start at the same point that the first user had started. And they will work sort of in lockstep through the table and complete. And what happens here is that they basically, one will pull the page in, the other one will grab it out of the cache, and they'll feed on each other, and it'll be a very efficient process. At the point at which the first user has completed his scan, the second user will come back in and pick up the rest of the table. So this is a little bit of a simplified explanation of what happens, but it shows you that by doing some work to make sure we're coordinating the scans, we can get the cache effect, we can reduce the disk thrashing. So again, in summary, we reduce the disk thrashing, we improve the cache behavior. Now, one thing that I should point out about this is that it only affects unordered scans. It won't affect ordered scans through the indexes. So that's important to understand. The other thing that's important to understand is that there's no synchronization that occurs between the various scan operations. And what I mean by that is that we don't, if one of the scans for some reason stalled, the other wouldn't stall and wait. It would continue on. So we don't have to worry about a bottleneck occurring if again, one of the scan operations or one of the user scans happen to be blocked for some reason. The reality is that they'll naturally work together anyway and sort of stay synchronized, but we don't have any code in place to make that happen. In terms of read ahead, read ahead is obviously a feature that we've had for many years, and certainly was in 7.0. We had a very advanced read ahead. I should say advanced and simple, and at the same time, it was advanced in the sense that our read ahead was very good at being able to read, make sure that we were prefetching pages that we needed to satisfy the consumers. But one of the issues with 7.0 read ahead is that, again, as we look at the larger and larger disk subsystems that are available in the larger SMP boxes, we realized that we needed to be able to issue more read ahead to keep the consumers of the pages busy. And so we basically implemented a deeper read ahead processing scenario. And what I mean by deeper is that we basically simply have more buffers available to prefetch into. And the algorithm is fairly straightforward. We use up to 1% of the available memory or buffers that are available to us, or 2,000 buffers, whichever is smaller. And the numbers we've come up with here are based on our analysis of the capabilities of the I/O subsystems today and tomorrow. The end result of this is that instead of having a scenario where you might have, say, an 8-way system with 4 or 5 terabytes of storage with 8 or 9 controllers on it, where if we could issue more I/O, the disk subsystem could absorb more I/O, but we couldn't give it enough. In this case, with SQL Server 2000, we can be assured that we can issue enough read-ahead I/O to keep the disk subsystem busy and to make sure we always have pages available to consume. And obviously, this is something that works well with SMP systems, improving our overall scale-up performance. Another area that I just put a brief note on here was integrated read-ahead during the recovery process. We actually have the ability now during our scans of the log records to prefetch log buffers, and then actually as we're working on a current log buffer, we can actually have read-ahead being issued ahead of time on the next log buffer, so that we could, when we get ready to process it, the pages are in memory and available. This has significantly improved our recovery times, and is certainly a feature that helps us in many areas, including our failover scenario. One of the last configuration parameters that we had in SQL Server 7.0 that most users had to potentially ever modify for performance reasons, and when I say configuration parameter, I mean SQL Server configuration parameters that have to do with performance, was the max async IO parameter. And I have my personal perspective on parameters are, configuration parameters are in the product because either one, there was no way to get the information you needed to configure it automatically or dynamically, or two, the developers just didn't spend enough time to figure out how to make it more automatic or self-tuning. In the case of the async IO, it was primarily because it was something that we needed more time to create the right algorithm to be able to remove that parameter and make that process automatic. So in SQL Server 2000, we've removed that parameter and put in place an algorithm which allows us to dynamically allocate asynchronous IO structures so that we are never in a scenario where we potentially are not driving the IO subsystem as fast as it can take IO. So in 7.0, the scenario was if you had a very large disk farm and you were using the default async IO parameter of 32, which controls the outstanding read and write IO, that you could potentially be in a scenario where the system would sort of look like it had an IO bottleneck, but if you check the latencies and the queue lengths on the disk farm, you'd realize that, well, there's no IO bottleneck, so why am I running into a scenario that looks like a disk bottleneck? And the reason was we just weren't pushing the IO subsystem hard enough. And so what you would do is you'd go out and you'd reconfigure this parameter to make it larger. Unfortunately, it wasn't always clear exactly what you would have to set it to. So again, in SQL Server 2000, we remove that parameter. We have an algorithm in place which allows async IO to increase with demand. And really the whole point of this is it's designed to allow the SQL Server to optimally utilize or saturate the IO subsystem without having you to provide input to the system. And again, there's just another feature that allows you to spend more time worrying about your application and less time worrying about how to tune the server. Large memory support, you've probably heard a lot about this already in various talks, and in the talk tomorrow or this afternoon on building high-performance systems with SQL Server, you'll hear more about it. It's a pretty critical feature. I'll just cover it real briefly from my perspective. In the scenario we have with SQL Server today, we can access up to 3 gigabytes of virtual address space. This is the limitation that NP gives us. But through some new APIs that are available in Windows 2000 called the Advanced Windows Extensions, we can actually access up to 36 bits worth of physical address space, meaning up to 64 gigabytes of memory if you could put it on the machine. It's implemented. The AWE extensions use a special mode in the Pentium Xeon chipset, which is what they call PA, or page address extension, and that allows us to be able to map and unmap pages between physical and virtual. So essentially, the short answer is that if you sort of watch the graphic here, you can see how we're sort of like, the green sort of represents pages we're working on, and as we need new pages that are in physical, we can map them into our virtual space. The critical point here is that we now have an integrated support for very large memory that is extremely efficient. The cost to map these pages between virtual and physical, or physical and virtual, is very light. It's very much lighter than, for example, copying memory pages back and forth between a secondary cache, which was a feature we had in 7.0 actually, but wasn't used very much due to sort of the limited usefulness of it due to the cost of the copy. But now we have a feature where even on a 32-bit system, we can very efficiently take advantage of memory beyond what you would normally be able to address. We see this as a stepping stone to being able to have a flat memory model of 64-bit. One point I will make is that this support is enabled via a parameter called AWE enabled that we have in SQL Server 2000. And once you enable memory, once you enable AWE memory, if you will, on a SQL Server 2000 system on Windows 2000, the memory is in fact completely non-paging. It's static. So that the thing to keep in mind there is that if you have other applications you want to run on the system, you have to keep in mind that by setting this parameter, you're consuming all of that memory in a non-paging mode for SQL Server. So you just have to think about whether this is a dedicated system or not, and how you want to divide the memory on the system. But again, it's very efficient. We actually used this support in a recent benchmark we did with Unisys, Unisys 8-way system running Windows NT or Windows 2000 Data Center. We used 32 gigabytes of memory on the system, and we're able to achieve over 48,000 TPMC versus with a 4 gig system only a little over 40,000 TPMC. So we got a pretty significant gain by adding the additional memory. One thing to keep in mind is just adding memory doesn't mean a linear increase in performance. If you double the memory, it doesn't necessarily mean you're going to double your performance. It means that you're going to get some percentage of gain if your workload has a locality of reference in terms of the data, or is, I guess I should say has a workload such that you're going to reduce your IOs in such a way that you're going to take load off the IO subsystem to maybe improve your overall cache effect. So your mileage varies depending on the application in terms of how much memory you need. The good thing is we've got plenty of memory for you if you need it. Checkpoint processing is something people don't often think about when it comes to IO, but the process of doing a checkpoint on a very busy system can affect the overall performance of the system, and it can affect it by introducing large amounts of IO onto the system, which is normally in a steady state, and that can disturb the overall performance of the system. So we did some work in in SQL Server 2000 to help reduce the overall effect of the checkpoint on a busy system. And in sort of a simplistic example up here on the slide, what we essentially do is when a checkpoint starts, the checkpoint will start and it will sort of mark pages as it starts walking through the buffer pool, and it'll start writing those out, the dirty pages out. At the same time, there's a lazy writer process which is constantly running and sort of freeing buffers to writing pages and then putting them back in the free buffer pool for reuse. And so the high-level overview is that as the checkpoint is processing through the table, it does not have to rewrite those pages. The lazy writer, in effect, is working cooperatively to help the checkpoint process. And the net effect of this is that you end up and again, the effect gets better as the system is more busy, because the busier the system is, the more pages are being brought in off from the disk, and the more work the lazy writer is doing to keep the free buffer pool full, and therefore all of that activity helps reduce the amount of IO that the checkpoint process has to do. It's a little more complex than this, but the basic scenario is that the checkpoint works more efficiently on a system with busier IO, with more IO occurring than it has in the past. And this is something we see as critical as we just talked about large memory support. So as the caches get larger and larger, the checkpoint process becomes more heavy, right? So this is a feature that allows us to balance to help make sure that as we grow our caches larger, that we're doing efficiently processing our checkpoints. Another feature which is sort of IO related and something that we're seeing as becoming more and more of an important area to focus on is how we process blob data, text and image data. And in 7.0 we did a lot of work in the area of improving the performance of how we deal with text. And one of the scenarios that we did in 7.0 is we changed the physical storage structure for text data from sort of a page chain to a tree structure, so that we could more efficiently navigate and update and manipulate the text data. And the scenario was that we had you have a text pointer off of the row that points to a root of the tree, and the text pages are sort of in the tree. In SQL Server 2000, we have this new feature called text in row, and text in row is very attractive for applications which have potentially a high number of columns which either don't have any text in them or have small amounts of text relative to the overall amount of data stored. The scenario is that if you have a text field that can fit in the row, meaning that there's room in the page, that you can literally store it in the page instead of having to jump off the page to go to a text page, essentially. If the text can't be fit on the page or in the row, then we will at least store the root of the tree. So we at least avoid the text pointer jump that we would have to do. The advantages of this are simply that you reduce I/O. You reduce the amount of I/O if you're scanning through text data and you have the scenario where a lot of text is small enough in size that it could fit on the 8K page. The thing you have to keep in mind about this is that if you're doing sort of non-text scans, if you can you can reduce the density of the rows on the page, and therefore you may actually have to do more I/O when you're processing, when you're scanning through a table than you would have in the other format. So because of this, what we do is give you the ability to control if you're going to store text in the row or not, and also if you choose to store the text in the row, if it fits your application, then we give you the ability to control how much, and that's called the inline limit. So you would enable, if you wanted this feature, you would enable it, you would set the inline limit, and you could control how much text is actually fit on the page. So this is really a great feature, I think, for today's applications, especially since we're seeing more and more applications incorporating this blob-type data into the applications for images and voice and video and so forth. The next performance challenge I want to talk about is processor and SMP scale-up, the ability to take better advantage of the CPU resources on a system and more efficient use of CPU resources. In the performance world, there's really two ways to improve improve the efficiency of how you use CPU resources. One is you simply eliminate code paths altogether, or through maybe caching of objects, so you don't have to go through those code paths again, or you just simply shrink your code path. You do a better job of optimizing the steps you have to take. In terms of SMP scaling, you do things like trying to ensure that you're reducing the amount of cross-processor cache traffic and contention. So reducing the amount of data sharing you have to do between CPUs helps improve your overall SMP performance. So in terms of solutions to those, I've listed a number of them here. There are obviously many, many more internally, but these are ones we think are pretty critical. One, we've done some work to help improve or to cache some of the most common operations that have to occur when we set up cursors. We have parameter caching. We've done some work in our inter-query parallelism to help our SMP performance. Something you've heard about probably a number of times already, parallel index creation, and something you probably haven't seen yet, but is an interesting improvement internally, is partition-free buffer lists. And we'll talk about those in a little more detail here. First of all, in terms of cursor side caching, cursors are a very popular way to access data in relational database engines, even though they arguably don't quite fit the model of how relational database engines were sort of designed initially to allow data access. However, they are quite popular and they're used quite heavily in many applications, and they have many advantages. The problem with cursors is that the process of setting up the cursor and creation of the objects and creating the plans and doing all the work you have to do to set them up is quite expensive in SQL Server 7.0. And so you end up spending a lot of cycles just preparing the cursor and building it up outside of just actually stepping through and fetching rows. So what we've done in 7.0, or excuse me, in SQL Server 2000, is to cache a lot of the information and execution plan for cursors, so that when you're using cursor operations, if you're reusing the same type of cursor, you don't have to redo that work. It's a very simple concept, but it's very powerful. If you have a workload that's dominated heavily by cursors, and there are many that are out there, you can expect a 10 to 15% reduction in CPU consumption for your cursor operations. So this is pretty dramatic, and you probably noticed that there are some world record numbers on the PeopleSoft HRMS and financial workloads, and these were one of the reasons why these numbers were improved so much was because they're heavily dominated by cursor operations, and this change has really helped those workloads. There's no application changes necessary to take advantage of this. It's one of these kinds of things where we're trying to make the product work more efficiently for you without having to change your application. In tomorrow's In the discussion tomorrow on building high-performance applications with SQL Server 2000, there'll be more discussion of server cursor caching and some of the other features that I'll talk about in the next few slides. Parameter caching. When you execute stored procedures that have parameters, most do, there is a fair amount of work that has to go on at the server to sort of check the data types to make sure things are in sync. There's also work that has to be done if you use default parameters in your stored procedures. There's work that has to be done to obtain what those parameter values of these defaults are. And this stuff all sort of occurs on the execution of the stored procedure. Being that is, again, an area of code that we could sort of eliminate or avoid by doing caching, that's exactly what we did. We cache the default parameter values and many of the operations that have to occur in terms of processing parameters. And the advantages of this are, again, obvious. You're eliminating code path, but if you have a workload which is heavily dominated by stored procedures, and if they do use many default parameters, you can see some pretty dramatic gains. A good example of this is in the SAP sales and distribution workload. SAP application heavily uses stored procedures, and they have stored procedures with many parameter values, and oftentimes many of those they simply allow the defaults to be used. And so in that particular scenario, we were seeing over a 6%, this is actually conservative, over a 6% improvement just through this one change alone. And again, it's a change that we've made in the SQL Server 2000 product, so that you don't actually have to do any changes in the application if you're using prepare and execute to call the stored procedures. That's the one sort of scenario where it's applicable. So again, a great way to basically do the same type of work but reduce the amount of code we have to execute, helps our SMP, or excuse me, helps our scale up on the processor. Interquery parallelism. We had interquery parallelism in 7.0. It was, I think, a very advanced algorithm. It wasn't based on necessarily partitioning data. It was more based on the idea that you would have, you would sort of divide the work that a query needed to do amongst the one or more of the CPUs that were available. I should say 2 or more of the CPUs that were available, and attempts to use the asynchronous nature, or I should say the parallel nature of I/O subsystems to feed those consumers. We did quite a bit of work on how our interquery parallelism based on feedback of the feature in SQL Server 7.0. We found places in the code where there were potential bottlenecks as systems got larger, as the number of CPUs on the systems increased. A number of them are mentioned here. Bitmap filtering is one area that was something that we could introduce a new technology to improve the performance. Elapsed time costing is an interesting one. It's in a scenario where we, rather than just determine whether or not we go parallel with a plan or not based on a cost threshold, we actually do a more intelligent comparison of the actual cost of the parallel versus the serial plan. Insert, update, and delete integration. We now, if the insert, update, or delete are being fed by operations which can be parallelized, then we will do that as well through the normal mechanisms we have today. In terms of what the effect of all these changes were in the TBCH workload, which is a ad hoc decision support workload that's created by the Transaction Processing Council, using these changes alone on an 8-way system, we were able to improve our performance in the workload by over 40%. Pretty dramatic. And we think that for applications that do make heavy use of interquery parallelism, they're going to be very pleased with these changes with SQL Server 2000. Parallel index create is fairly straightforward. The index creations in SQL Server 2000 are now handled much like normal queries are handled, in the sense that when you execute the index creation, it goes through the query processor and it will be parallelized like any other query. The scenario in SQL Server 2000, when you create the index, the first thing we do, as we do with any query that we run in parallel, we determine how many CPUs we should use on the system by looking at current activity, a degree of parallelism, if you will. The next thing we do is we define partitioning functions per CPU that are used to filter rows for the process of building the index. If the table has indexes on it, we'll use that information to define the partitioning functions. If it doesn't, we'll actually collect statistics on it prior to the creation of the index. Once those partitioning functions are defined, we start scanning the base table, and the scans are fed back to these partitioning filter functions. The scan is actually similar to the merry-go-round scan in the sense that all the CPUs are scanning, but the IOs are sort of, you're getting the cache effect of one scan picking up the IO and the other one using it out of the cache. Anyway, those scans are passed up through the partitioning functions, and then we sort of filter out the rows that don't apply to our particular portion of the data that we're interested in. And then, of course, the indexes or the results are all merged up to create the index. So that's sort of internally how it works. In terms of how effective it is, it's extremely effective. Anyone who's had to sit through and watch an extremely large index, create an index in an extremely large table and watch how you watch it and you see like one CPU in the system pegged and you're going, geez, I wish I could take advantage of all these resources. Well, this type of a feature does that, and it's something we've really needed for some time, and we now have it in SQL Server 2000. When I say linear scaling, it's very easy to back this up. We have a very large table in our TPCH workload, which would take about, on a large scale system, about it was like a 300 or 400 gigabyte database. It would take us about 4 hours to create that index on an 8-way system. We cut that into about 30 minutes, a little over 30 minutes. So using this feature. So a great feature for being able to improve the manageability of our system on large S&P boxes. Partition-free buffer lists. I put this in here. This is one of those kind of things that we did internally in the product that you probably would never know it was there, because there's no application interaction with it. It's an internal sort of plumbing thing we've done. But I put it up here to tell you a little bit about it, primarily because I think that it demonstrates our commitment to using very advanced techniques and algorithms in our product, cutting edge really, to make sure that we're keeping up with technology and being able to take advantage of hardware very efficiently. In SQL Server 7.0 and with previous versions of SQL Server, we maintain something called a free list, and the free list is essentially a list of buffers in the buffer array which are currently not used. So when somebody needs to pull an IO off disk, we go to this free list. We have some work. We have to lock down our access to it. We grab the free buffer. We read the IO. We hash it, and then it becomes accessible for ourselves and anyone else who might need it out of the cache. As the number of CPUs in systems gets larger, the contention for the free list access increases, and that affects your scalability. It also is true that the free list is shared by all of the CPUs, so you get sort of a randomized effect of when you grab a page, that page may have been on CPU 4 and you're now on CPU 1, so you have this sort of cross traffic occurring. With SQL Server 2000, what we've done is implemented free lists per CPU. So we've effectively removed a lot of the contention on the free list access, and at the same time enhanced our cache locality. One of the interesting things about this architecture is that because we still have this process of the lazy writer, which sort of runs around and makes sure that there's a number of free buffers available by flushing pages out that haven't been used in a while. But we now allow we now distribute the process of lazy writing to any user. So any user who's doing an I/O may be required to do some lazy writes as part of his operation. So what ends up happening is that the population of the free list is such that it sort of stays affinitized to the particular, so softly affinitized to the CPU you're on. So you get sort of a natural you get a scenario where you're sort of one CPU, the user on the CPU are using the same pages over and over again, so you're reducing the amount of cross CPU traffic. This is an architecture which will continue to advance as we go forward. Again, I mentioned earlier that we had sort of the plumbing in place to continue to do very advanced modifications in the server as new hardware technologies come out. This is a feature that is, you could imagine how this might make a NUMA-style platform more efficient, and with some additional enhancements, we could get to the point where we could almost literally partition completely between CPUs or chunks of a NUMA machine. So this is basically an internal change that has definitely helped our SMP scalability, but again, it's something you get for free. It's underneath the covers, but again, demonstrates our ability to be able to do very advanced work architecturally inside the server to solve some of these types of problems. Network I/O is a huge challenge for us. The types of applications and systems we're seeing being built today is just incredible. We have, obviously, beyond two-tier, we have in-tier apps. We have apps which actually have fat clients, which not only go to application servers, which then go to the data tier, but they actually will go out to the data tier directly. So you have very complex networking structures, huge numbers of web servers in front of the data tier. All of this, of course, being driven by e-commerce style applications. And it's just really putting in a huge load on the network. And one of the sort of side effects of all of this is not necessarily that the network bandwidth, that you can't handle it in terms of network bandwidth, but that there's a tremendous amount of CPU cycles being spent on the actual systems just processing I/O. And so how do we deal with all of this? Well, we have some techniques in SQL Server 2000 that really help improve how we deal with this sort of explosion of network traffic. And one of them, there's basically three scenarios that are critical. One is, how can we reduce round trips on the network, having to go back and forth between the application and the data tier? How can we reduce the amount of data we send back and forth between the data tier and the application tier to do a particular piece of work, which is reducing metadata? And the final is, how can we take advantage of new technologies that are available in terms of system area networks and networking infrastructures that allow us to get significant benefits due to newer hardware and newer switches and so forth. So let's talk about this in a little more detail. One of the areas that, in terms of reducing round trips, is prepare and unprepared caching. So if you're using a prepare execute model, we have a technique where we no longer need to take a round trip between the application and the server to actually do the prepare. We actually cache that prepare and send it on the first exec of the query. And the same is true of the unprepare. We would piggyback it on the next prepare so that we don't actually have to take the cost of unpreparing. This is something that will be talked about, again, in more detail in the session tomorrow on building high-performance applications with SQL Server, but I wanted to just briefly mention it in the sense that it is pretty critical as the amount of work is increasing and the number of transactions are increasing into the data tier, that we do everything we can to reduce the amount of times we have to communicate back and forth to do the same amount of work. The one thing that the comment up here about overall benefit inversely related to increased in execs of prepared plan is pretty obvious. You're saving basically 2 round trips, the prepare and the unprepare. If you were to be executing the plan 1,000,000 times, obviously that cost of the prepare and unprepare is very small relative to the total work being done. However, if you're executing the plan 5 or 6 times, the extra 2 round trips can be quite significant. So you sort of think about it in that scenario. The good thing here again is that it's something that you get for free as long as your application is designed in such a way that you're binding before you exec. Metadata caching, again, the idea of keeping data off the wire. It's a pretty straightforward scenario. We just have logic between the client and the server that helps ensure that we don't need to send metadata about data types and structure between executions if it hasn't changed. In the case of having large numbers of columns being accessed in a query, it can be quite dramatic, the improvement. There's about 10 bytes per column we estimate that is basically for metadata. You can, with this scenario, that goes away. You reduce the amount of data on the wire by that amount. So for example, if you had 100 columns being passed back and forth at 10 bytes, you're talking about a K on the wire you're saving per operation. So it can be quite significant. The bonus of all of this is that there is a cost associated with just processing metadata in terms of CPU cycles on the server and the client. So that's something you also avoid. You avoid data on the wire. You also avoid the CPU cost of processing it at the client and the server. And one estimate we did was in our labs was with a table of over 50 columns, we were able to, or an axis of over 50 columns, we were able to reduce the cost by about 10% in terms of CPU. So that's pretty significant to any application. System area network support. So outside of doing our work to decrease the amount of data on the wire and to decrease the amount of round trips we have to take, the other critical thing is being able to take advantage of very advanced enterprise class technologies in terms of networking. There is support. We basically did some work in our SocketNet library to support the WinSock Direct feature of Windows 2000 Data Center. That is a feature which allows the vendors of these very high performance network architectures to be able to create providers and allow standard WinSock applications to be able to use that technology without modifying their app. So we support that in SQL Server 2000, but we went a little bit further. We actually wrote several native network libraries, and the network libraries are the piece of code which insulates SQL Server from the network protocol. We wrote several native network libraries for the VI, Virtual Interface Architecture standard, and specifically we wrote one for ServerNet 2, compact ServerNet 2 technology, and also for GigaNet CLAN technology. Now, if you're familiar with this technology, one of the advantages of it is that it offloads a lot of the TCP/IP processing off of the system and down into the controllers. It takes it out of the space of the kernel within the operating system, and this can be obviously there are big performance benefits of this in terms of reducing the amount of CPU, but the solutions typically offer very high bandwidth, low latency. They're very reliable, and as I mentioned earlier, there's a reduction in CPU overhead. Where we see big advantages for using this type of technology is very network intensive interactions between the client and the server, which is something we see a lot in ERP style applications. It also is advantageous if you're in a distributed scenario where you've got distributed transactions occurring between the data tier. This type of technology helps reduce the latency between the machines. In the case of our recent SAP benchmark that we published, we were able to see reduction by using the ServerNet and GigaNet technologies. We were able to see reduction in kernel time of about 1/3, and that equated to a 20% plus increase in the number of users we could support in the system and still retain a response time of under 2 seconds. So pretty dramatic change. Your mileage sort of varies with this type of technology. If you have an application which is more heavily I/O limited, or I should say more heavily doing much more I/O, disk I/O versus network I/O, then this is going to be less of a benefit. If you have an application which is doing a tremendous amount of network I/O versus the amount of disk I/O, it can be quite significant. Again, support for advanced technologies that allow us to be able to support very large applications. I want to take a little bit of time to talk about the performance challenges of the increased data and query complexity. And I mentioned earlier, and it's fairly obvious, that in today's world we're collecting tremendous amounts of data, much more than we ever have had in the past in traditional transaction processing systems. And we're doing all sorts of interesting things with this data. We're moving it into data warehouses. We're doing very complex queries on it. We're trying to dig into this data to figure out what to do with it. The data itself its nature, the distributions of it, the skew, are also quite complex. And so how do we deal with all of this? Well, we have a number of solutions in the server, in SQL Server 2000, for dealing with this increased amount of data and query complexity. One of the most important is that we've done a lot of work to improve the process of how we collect statistics and how we represent them. We have done work to take the already powerful query processor in SQL Server 7.0 and make it even more powerful by improving the efficiency of many plans. We've done a lot of work, as Lubor Kohler mentioned in his session, I think yesterday, on enhancing how we use indexes and what types of indexes we can create. And finally, one thing that's not often thought about in this scenario is we've done a lot of work to improve how we handle mixed query workloads in terms of complexity. Very complex queries at the same time being executed with less complex queries, and how we balance the system. And we'll talk about each one of these in a little more detail. In terms of what we've done around statistics, I actually believe this is probably one of the most important changes that we have made in SQL Server 2000 in terms of performance. Oh, sure, there are some other flashy things like distributed partition views that are really cool, but this one is a fundamental change in improving the input that we give the cost-based optimizer to make decisions about how to generate plans. Cost-based optimizer obviously is only as good as the information it gets. Information about the table structure, about the indexes that are available is fairly easy to obtain. Information about the nature of data, the distribution, the skew is more difficult to obtain. And this change is all about making the representation of or the understanding of the data more granular, so that we can do more work with it. The actual change here was that in SQL Server 7.0 we would create we had a very efficient mechanism for creating statistics, but we would create an equidepth histogram for the statistics on the statistics page. And as we wanted to use that, we'd have to do some processing on it and modification and changing it to put it into a form where we could actually use it for costing, and that obviously costs some cycles. But also, in the process of doing that, we lose some granularity of the statistics. So some things like trying to handle very skewed data, we could potentially lose information that would maybe potentially every once in a while cause the optimizer to make a mistake in terms of a plan. So what we have now is this really, what I think is one of the most advanced algorithms in the industry, where we create a max diff histogram for statistics. And essentially what I mean by that is we dynamically determine our bucket boundaries as we're sort of passing through the data that we're going to be using to collect the statistics on. And again, this particular algorithm is very efficient at handling, very good at capturing skew in the data, which means that it improves our cardinality estimates, it improves the overall granularity of statistics, plus the data in the statistics page is actually in a form that's more easily usable for us, so we spend less time sort of processing it before we use it for costing. One of the things that comes up when you think about the fact that we've changed how we store statistics is that what happens if you upgrade a database. If you have a very large database, it could be quite expensive to upgrade the database and have it actually go through and upgrade all of the statistics. The way we handle that in SQL Server 2000 is that we don't actually update the statistics as part of an upgrade. Rather, what we do is our query optimizer is smart enough that it knows how to use the older statistics format. So basically, everything will work the same. Over time, if you have auto-update statistics enabled, the statistics will naturally upgrade to the newer statistics if there's modifications and things occurring on the table. If they're static tables, that wouldn't occur. Of course, if you have the ability and you want to see an immediate advantage to the newer formats, you could update all the stats in the table on all the object, or on the database on all the tables, by using the SP update stats procedure. So we're thinking, we realize that changing the statistics is incredibly important, but we want to make sure that we can amortize the cost of it over time for people who are upgrading their databases. This particular change has had some pretty dramatic effects on some databases internally at Microsoft that we use to track all of our sales. that particular, we call it the MS Sales Database. It tracks, again, all of the sales for Microsoft, and it has some very unique characteristics in terms of the nature of its data that caused occasionally SQL Server 7.0, which, by the way, is just an awesome query processor in terms of how it does costing, but even it was fooled a couple of times. And so this change has allowed them to make significant gains in their improvement, significant improvements by coming up with better plans, again, because the inputs are better. So I've talked a little bit about the fact that we have more granular and accurate statistics, and this improves the input to the optimizer, which means we make better choices. One thing I want to comment on, without getting into great detail, is just the fact that when we built the 7.0 query processor, which is the core of what's in SQL Server 2000, it was designed to be modular and flexible so that we could, without rewriting massive amounts of code or making massive changes, we could, if we found a scenario where there was a particular query plan that was being generated that you know, it's just not working the way we wanted to, we could very quickly go back and sort of rearrange the building blocks and make it do the right thing. And so we did quite a bit of work of that in SQL Server 2000 in terms of making sure that the query processor, I call it fine-tuning, if you will, fine-tuning for complex queries. So when we found a case where a wrong, incorrect plan was being chosen, probably many of you found those, we would be able to quickly make the modifications necessary to handle that in the correct way. And part of that was also, part of the changes we made in that area was also to do a better job of handling trivial cases. Even when we shipped SQL Server 7.0, we had done a lot of work to make sure that if a plan was fairly simple, that we wouldn't spend a lot of time going through a huge search space to try to find an optimal plan. But we've done more of that. We found even more cases where we could say, you know, we have this really advanced query processor that knows how to, you know, has all this information available to it, but guess what? This plan is so simple that rather than spend, you know, the 50 milliseconds coming up with an optimal plan, let's just take the one we get right off the bat and we'll probably come out ahead. So we do more of that in SQL Server 2000, and that's turned out to be a big improvement as well. Index views. How many of you actually saw Lubar's session the other day on index views? Just have an idea? Okay. He did most of you. He did a good job of explaining these. He's obviously the program manager for index view support. I'll just spend a few minutes on it for those who didn't see that session. Index views are a feature in SQL Server 2000, very similar to some other technologies that exist in the market, materialized views, join indexes from Teradata. But basically what they are is the ability to create an index on a view, and an index can contain joins and aggregations or some combination. The index, once it's created, it persists so that you can effectively take the cost of very complex queries and materialize it into a static structure and index so that when you need to reaccess or do a similar type of query operation, you don't have to do all of the work involved in processing all of the aggregations or whatever other things you might be doing. One of the neat features about index views is that even if you don't actually reference them in your application, you can still get the advantage of them. They're still available to you. The optimizer is smart enough to know that it can go out and find them. And the cool thing about that is you know, even if you have an application today and you don't have the ability to change your queries to reference the views, you can put these views on and just see how they react. You can do experimentation and find out where they're beneficial and not beneficial. The most important aspect about materialized views that you understand is that they're a great feature, but you have to be careful about where you use them because there is a cost associated with maintaining the views, and it's a higher cost than a traditional index because again you're materializing things like aggregations and joins. At this time, it's not really possible for me to give you information about where the break point is, about what exactly, where exactly you'd want to use an index view versus not an index view. But what I can tell you is that our traditional decision support style system, data warehousing, a business intelligence system are the scenarios where you would be using index views potentially that would help reduce your query times significantly for these complex operations while at the same time there wouldn't be very much write or update activity going on in the data, in the tables. So if you haven't seen Lubar's session on indexed views, I think it'll be on the post-show DVD and you should watch it. He goes into much more detail about them and some of the restrictions and limitations and advantages of them as well. One of the areas I mentioned briefly earlier, and you probably looked at it kind of scratched your head, what is that multi-user robustness? What exactly does that mean? Performance is not always about shrinking code path. I said earlier that was what it was all about. Well, it actually isn't all about that. That's really important, but it's also about making sure that the components in the system, in a complex system, are working well together, that they're cooperating for the overall good of the application, if you will. In SQL Server 2000, we've done a lot of work internally in how we schedule queries through the query processor. We do a better job, a more intelligent job of looking at a mix of queries being presented to the system and saying, every query you execute has a requirement for some amount of resources, whether it's memory or CPU. And so what we do in SQL 2000 is we do a better job of sort of intelligently looking at what resources are available at the time we're executing a query, and whether or not we should execute that query now or maybe wait till some additional resources free up. And an example of this would be you execute a query that you know it's going to take a long time. It's got to plow through a whole lot of data. It's got a lot of complex operations. It could take hours to complete. If you were to execute that query, and if it were to be scheduled right away, and at the same time there were many other queries executing that were currently consuming all of the available memory or resources on the system, if you just let that query go, he would get some portion of the amount of memory available in the system, and you'd go off and try to execute it, and it could take a long time given the resources it has to complete. Whereas if we were to maybe wait a little bit, wait for some resources to free up, then start that query, it would actually execute much quicker, and the whole system would run more efficiently. That's the kind of logic that's built into SQL Server 2000, and is I think a pretty dramatic improvement over what we already had, which was in 7.0. One of the benchmarks that we use to look at complex query performance is, again, I mentioned TPCH, which is again an ad hoc decision support workload. One of the things about that workload is it requires you not just to run one stream of transactions, but you have to run multiple streams, running the same set of queries in a different order. So you have some very complex and some less complex, and they have to interact together. And that's a really hard workload for a lot of database engines to handle. By making these types of changes, making us more intelligent about how we schedule work, we were able to make dramatic improvements in how efficiently, in the overall performance of the system as a whole. So enough said on that, but basically this is a subtle change, a subtle but powerful change in SQL Server 2000 in terms of how it cooperatively deals with these mixed query complexity sets. I had to put this slide up. Everybody's shown this slide already, but I'm going to put it up because my performance team worked pretty heavily with our development group and with our partners on generating these results. The point of this slide is that I talked about the fact that scaling up CPU resources was one of our objectives. This is, in this particular scenario, we had the same 8-way platform, same 8-way compact platform with the addition of ServerNet 2 networking technology, and we were able to increase our performance by over 50%. 50% improvement on the same hardware. Same application workload, didn't change the application workload at all. This is all about reducing code path, being more efficient in how we schedule work on SAP systems, and taking advantage of advanced technologies like the ServerNet 2 system area network support. And we'll continue to do this as we go forward. I've got about 10 minutes left, and I'm going to talk a little bit about the performance challenge of scaling the data tier out. And this is something that's been talked about in quite a few other sessions today, or over the week, I should say. The whole idea is that no matter how good of a job you do about making performance improvements to scale up and utilize CPU resources efficiently, at some point you run out, and you need to be able to spread your data tier workload over multiple servers. And there's a variety of things you have to be able to do when you talk about being able to scale a data tier workload out over multiple machines. How do you coordinate the transactions? How do you intelligently distribute the queries? And so forth. In SQL Server 2000, we build on top of building blocks that we had been working on for years. We have a solution today for building high performance and highly scalable scale out applications at the data tier for particular types of applications, I should say that. But we didn't just build this all at once. What we did was we have been building for years different building blocks with the overall goal of being able to do this. And with SQL Server 2000, we exposed a particular feature called distributed partition views that can be used over the top of technology has already existed. OLEDB, distributed query support, our DTC, our distributed transaction coordination, all of these things that already existed, we basically put this feature called distributed partition views on top of that, which now gives you the ability to have a transparent DML or access to tables. There's a session tomorrow, as I mentioned, in the afternoon called Building Scale-Out Applications with SQL Server 2000. I highly encourage you, if you're interested in this area at all, to go to that. There's been a lot of sessions giving overviews of this, but that's the session where they're going to go into in gory detail about what it means to build an application and what types of applications are best suited for this type of technology, because there are some applications that are well suited for it and some that are not. The basic idea, though, of distributed partition views in terms of a summary of it is that you're able to create a union-all view over one local table and one or more remote tables. And the neat thing about that is on different servers, and the neat thing is that that's an updatable view. So you have this full update, insert, delete, select tool set that you can apply to a single transparent view of a table that may lie over multiple member servers. And of course, we do things internally. You're required to have a check constraint to make sure that you have disjoint partitions of the data on a particular partitioning column. Underneath the scenes, there's technology like OLEDB, linked servers that are allowing these guys to communicate. The best way to think about this is that if you have a workload that is inherently partitionable, for example, you have regions, you have West Coast, Central, East Coast. You could potentially, if it's possible, you could potentially partition your data so that you're routing transactions to the region, your local region most of the time, but occasionally if you had to go out and access remote data on another region, you'd have this ability to do that. And you could do it through the view without changing your application logic, without having to build in the logic to say what member server do I go to in my distributed system. And I'm going to leave the discussion around distributed partition views at that level. And again, I encourage you to go to the session tomorrow if you can, to get really the inside scoop on how this all is put together. It's actually quite simple. We used this technology along with the other building blocks I'd mentioned recently to generate the world record TPCC benchmark, which I'm sure you've all seen many times. I wanted to give you a visual picture of what the system that we used to do that world record result looked like. This is a photo of the lab in Houston where we worked with Compaq for about 3 months on generating this world record result that was a distributed TPCC or clustered TPCC result using our distributed partition view services that we have in SQL Server 2000. And it's essentially, the system essentially is comprised of 15 racks of storage slash 8-way servers. It's quite impressive to see it all functioning. And what was really, I think, neat about this particular result is that we did it in such a short period of time. I mean, the hardest part about this benchmark was actually putting the hardware all together. In putting the software on top of it and creating the views and creating the distributed tables was actually not that difficult. The system itself, as you can see, if we wanted more performance on this particular benchmark, we would just add another node. We could add another slice and get some more performance. The particular workload that we use, that's used in TPCC, is an order entry workload that uses a warehouse as a partitioning sort of value, and so it lends itself well to this type of an architecture, which is also true of many e-commerce applications as well. There's no reason why this number couldn't be much larger. We figured 12 was enough. We had a world record, and we really didn't need to go any farther, but it can certainly go farther with fairly simple changes. You could add another node, you could build another table, add the check constraints, update the views, and you instantly have another piece of the database online. From a comparative standpoint, you've probably seen this already. I'm just going to skip by it, but essentially we're obviously very proud of these results, and we think they're quite impressive compared to our competition. The 135,000 TPMC was the largest result on an IBM platform up until we did this result. So that's really the end of the session, and I've listed here some other sessions. Many of these have already occurred. I encourage you to, if you haven't seen these, these all have sort of performance focuses. You can see them on the post-show DVD. At this time, I think that we're a little bit early. We're about 5 minutes before the end of our session, but I'll entertain some questions if anybody has them. Do we have I think we have a microphone up here, if anybody's interested.
One is, in the old way of doing memory swapping, we would copy. It would, you know, in SQL Server, when you run address 1 or 4 gig, you would have to do like copy, so it would cost you more. Now mapping on mapping supposedly was going to cost you less. How much less is that? I mean, can we, because before we tend to tell customers, well, I'm from Microsoft basically, tell customers not to really use above the 3 gigs for SQL Server because it would be a really a good sizable cost.
Right. Just so real quick summary, the question has to do with the cost of copying memory out of a secondary cache versus this mapping, unmapping scenario that we use with SQL Server 2000. In SQL Server 7.0, we had this thing called the PSA36 driver, which was a driver that we were able to access through SQL Server 7.0 to access a secondary cache that was provided through this driver. But in order to do that, we had to do copies in and out of that secondary cache. And the types of applications that benefited from that were quite small. And the reason why they were small was that the cost of the copies is linear. It just contains, you just keep piling up the cost. We would typically see cases where it was advantageous if you had a underpowered I/O subsystem, right? So that you could afford to trade the cost of the CPU versus the I/O. Reality is you could probably take that same system and just put bigger I/O subsystem on it and get equal or better performance. So it really is a sort of a stopgap approach. In SQL Server 2000, that issue no longer exists. The copies, the maps are, when I said they're a magnitude less, that's exactly right. They're a magnitude less. Could I draw you a curve and tell you exactly how that relates to a full flat 64-bit model? Not really. It's difficult to do that, and it depends on the workload that you're using. But I can tell you that that they're extremely efficient. In a 32-bit space, or a 32-bit operating system, this is as good as you can get in terms of accessing memory above the normal virtual range that you're allowed. So we see this as a great step. We've proved that it's beneficial by using it in a high-end benchmark. In fact, to give you an idea, on the TPCC workload, which again, you have to understand that it's very high I/O heavy, and it's not, you know, every application is different in how it terms of uses memory, but we were seeing about a 10% gain in performance for every doubling of memory, all right? Now, as I said before, just doubling memory doesn't mean you're going to double performance, but a 10% gain by doubling memory is actually quite interesting. And again, that's specific to a particular workload. So that, I don't know if that answers your question, but it's a very efficient mechanism, and it's, like I said, it's the next best thing to full 64-bit support that we're going to have.
I have two more questions. Another one is a number of connections. We have a hard-coded 32,767. Is that ever going to be removed?
The number of user connections?
Yes, because I have a .com company that went pretty close to 16,000 already, and they're wondering if.
Are you talking about concurrent connections into the database engine?
Yes.
Okay, I'm not actually, to be honest, I'm not aware of the 32,000 plus connection limit. I didn't realize we actually had one, to be honest. I'm not too surprised, but I wasn't aware of it. What I can say is that anybody who is really subjecting the database server to that many concurrent connections probably needs to rethink their architecture a little bit, because in reality what you probably want to do is use a sort of a MTS or complex model where you end up pooling connections to the server and have fewer connections. The reality is that if you have 16,000 users attached to a database server, in the real world, you probably only have a couple hundred of those actually executing anything at one given time, slice of time. And so you're really just wasting resources on the server by maintaining those network connections and the memory associated with the connection. So I would suggest that a user like that move to a model where they're multiplexing their connection access to the data tier through Com Plus or some other transaction monitor.
Well, basically they're doing that. They're using MTS, and with object pulling on, we were able to. We at times get as many as 16,000 on it. That's why the concern came up.
Yeah, there must be something in that architecture that is not allowing proper reuse, because there's no way I can believe that that they would, if they were pooling connections, that they could be achieving 16,000 concurrent executing operations at one time. I would just encourage you to go back and maybe look at that architecture a little bit closer and see whether or not it's truly concurrent connections to the database server or not.
I see what you're saying.
Yeah. As far as the limit goes,
Right.
outside of that sort of piece of information, the limit itself, I don't have the answer for that. It's something that if you want to send me a question in an email format, damienl@microsoft.com, I'll certainly get back to you with an answer on it.
Sure, because I think Oracle doesn't have it, according to them, and they're just kind of like wondering why we have to put a limit on it.
Well, I can tell you that Oracle, I would doubt that Oracle would even be able to run with 16,000 direct connections. They have a very different architecture, which is much heavier in terms of connections. You have to almost multiplex in that scenario. So.
And the third question I have is, I noticed that you're using 4 gig in your scale out results for your world record. You're using 4 gig per server. Was there a reason not to use more memory per server? Trying to use mapping on mapping?
Yeah, that's actually a good question. It's very, very observant. There was a couple reasons why we didn't use the more than 4 gigabytes on the server. There's a cost you pay in a scale-out solution, and the cost is that you have a lot of extra work to handle the distributed processing, and so you get your overall performance on a single node is lower than it would be if you were running just a single node. Because the performance is lower on the distributed nodes, you get more headroom, right? But you pay a cost. It just so happened that the amount of work that we would end up doing in this scenario was such that the I/O subsystem could easily handle it, and adding more memory wouldn't have been a big advantage to us. There's a couple other reasons that are more sort of scheduling related. It would have required using data center version on the member servers, and it wasn't quite in a state where we wanted to use it at that time for the benchmark. But we did use data center with a larger amount of memory for the single node Unisys TPCC result that we released that was about 48K. All right.
Damien, getting a couple questions from some customers on how we do that scale out, and they're starting to drill underneath the covers a little bit, and they understand partitioning the table. They're buying off on that. But what do you do with the tables that you don't need to partition? Like, let's say it's an order entry system, so order header, order details, I partition that out and do a range partitioning. What do I do with like customer, product, that sort of a thing? Did you guys use like an immediate updating subscriber and actually partition those as well? Or did you keep them on one server and just for those commands or those operations go just to that one?
It's a very good question, and actually I didn't talk to it, but there was a comment on one of my slides that said instead of triggers. I don't know if you saw that. There's a number of ways to handle the scenario you're talking about, which is a table that is sort of doesn't need to be partitioned, but needs to be sort of maybe a read-only or a static table that everybody needs to access. In the TPCC benchmark, there's actually a table just like that. It's called the item table. The item table is a read-only sort of table. It contains basic information about the items that you maintain in your warehouse. And what we did in that scenario is the table itself is relatively small, and I think 100,000 rows. What we did was we keep clones of that table on each machine, then we use instead of triggers to say if somebody ever updates that table, we make sure that we go out remotely and update all the other tables. That's one way to handle it. Another way would be replication services potentially. Another way to handle it would be to actually have another server that actually had that table on it, although you'd end up potentially with a bottleneck on it. The neat thing about this scale-out scenario is that it's a federated scale-out scenario in the sense that you have symmetry between the partition table views, or distributed partition views, but it doesn't mean you couldn't have other systems doing other work in the system. So I think the real answer to that is potentially maybe use a scenario like a distributed or like an instead of trigger or a replication service to handle it. Well, the instead of trigger would do a remote update of the other tables via DTC, which would give it a two-phase commit. I mean, right, absolutely. Under the covers, it would use that. Any other questions? Okay, thanks.